I'll talk about resource allocation problems in communication channels. So there's a fancy name for a communication channel, multiple access channel. What it simply means is that there are multiple transmitters or multiple agents in a particular communication system, and they are all trying to talk to a particular receiver. To give an example, let's say you have a lot of mobile phones in this room, right? And they are all trying to talk to one access point. And what we call this channel or this communication system is a multiple access channel. Why we call that as a multiple access channel? Because there are multiple cell phones trying to talk to a single access point through this air medium. So this channel is the air medium, and multiple devices are trying to access that access point through one medium, and hence the name multiple access channel. Okay, and this is the general block diagram we use to represent any multiple access channel. There are multiple transmitters, or we'll say transmitting agents. Okay, in this case there are capital N of them, and they are trying to access or trying to talk to one particular receiver, for example your access point, and they are trying to talk to the access point through an air medium which does something to your signal. It distorts the signal in a certain way. Okay, and this distortion we model through a channel gain. So basically if you send some signal, what it does is it some sense attenuates the signal. So there is some gain to it. We call it as a gain, but in actual terms it's not a gain. It reduces the signal amplitude. So there is some multiplicative factor, whatever that signal you transmit, there is a multiplicative factor, and then it all gets added up because it's an air medium, everything goes to the same spot. So N transmitters transmitting or talking to a single receiver through the air medium, each having their own attenuation, what we'll call as channel gain, and then eventually it's all added up at the receiver. In addition to all the signals that are from the transmitter, there is a noise at the receiver. This is because of electronics. There is some restriction in the electronics. You always have some noise at anything you try to acquire or observe. There's always some noise added to it. You never get really perfect signal in real life. So there is always a noisy version. So what we observe is a noisy version of the sum of all these transmitted signals. Now, in general, most systems that you see, you would have always seen the noise to be modeled as a Gaussian noise. But it so happens that it's not really a good model in reality, and we always use Gaussian noise simply because of central limit theorem. You have multiple factors and multiple random variables, they all add up together at the receiver or at some point, and then we say that they're all independent random variables. There are a bunch of them. So from central limit theorem, we are safe enough to call it as a Gaussian noise. But it so happens that it does not really is the case in reality. There is always some dependency on the random variables that get added up. And it so happens the generalized Gaussian noise is generalized Gaussian distribution is a much better distribution to model noise in reality than the Gaussian distribution itself. Okay? And this is how the generalized Gaussian noise looks like. The distribution of the generalized Gaussian looks like this. So there are two factors here. One is the scale parameter gamma and the shaping parameter beta. So the way you change your beta actually determines what does the actual distribution look like. So if you set beta is equal to 2, we end up getting the Gaussian distribution itself. And if you set beta is equal to 1, you get Laplacian distribution. And as you increase beta more and more, it becomes more and more localized in its support. So this so happens to model a lot of practical scenarios where we have a much smaller support for this distribution of the noise than the wider one which is supported by the Gaussian distribution. So this seems to model a lot of practical systems, especially communication systems, a little better than the conventional Gaussian. Okay. So we'll say that this is our model, and this is going to model a multiple access channel, for example, like a Wi-Fi system or your cellular system. And then the problem that we are trying to address here is how to choose how much power should I put in transmission at each of these agents so that there is some reward that is maximized at the receiver. The reward that we'll say is the data rate. For a communication system, I want to achieve the maximum data rate possible. So let's say there are multiple of us trying to transmit something to the access point, the Wi-Fi access point. So each our cell phones have some battery amount, right? So we can transmit all the power that is present in our battery, or we can use some portion of it. And then eventually, all of it receives the access, all of it goes to the access point, and at the access point, this power gives us some data rate. It can be some 10 Mbps or 1 Mbps or whatever. So what we are trying to do is we are trying to maximize the total data rate. When I say total data rate, it means the sum of all data rate of all the mobile phones that are transmitting here. So that's what we'll call as our objective here. So the objective here is to maximize the sum rate, sum of all data rates of all individual users. So clearly if I have put in more power, then my signal will be much stronger, so I can get more data rate. But then what is the adverse effect of this is that the more power I put in, it's going to look as noise, or it's going to appear as noise for another user. So in other words, this is the model that we have, where Y is the received signal and W is the generalized Gaussian noise, and SI is the signal transmitted by the ith user, and HI, capital HI, is the channel gain of that particular user. So everything gets added up. So how do the receiver decode a particular ith user signal? So each of the signal of each of the user has to be identified at the receiver. So the receiver access point has to know what user A transmitted, user B transmitted. So it is going to decode each of these transmissions by assuming the rest are all noise. That's how it's going to decode. Which means if one particular user puts in a lot of power, then that's going to appear as noise for another user. Okay? So the more power you put in, it might appear as if the data rate is going to go up for you, but it's going to look like a very high noise, or the noise power is going to look very high for another user signal. So in other words, if everyone starts transmitting with very high power, there's going to be a lot of noise at the receiver, and the total sum rate will actually come down. So it doesn't mean that the more power you put in, the higher data rate you will get. Because of the nature of the multiple access channel, the more power each user puts in, the more interference or more noise every other user sees. So the total data rate of the entire system comes down. So what we want to do here is we want to maximize the data rate such that we want to choose the powers for each of the user's transmission such that the total or the sum rate is maximized. So that's our goal. So some assumptions for the system models here, we are going to quantize, or we are going to discretize the possible channel gains each user can see. We'll say that there are only capital D number of channels that each user can see, and we are going to say that, that's a discrete set. And this is a random variable. So let's say I move around this room. The moment I move around this room, my distance between me and the access point keeps changing, which means the amount of attenuation the signal goes through keeps changing. So hence the channel gain is a random variable. And it's actually a Markov random process. The channel can be modeled as a Markov random process, but we'll focus only on the stationary distribution of this random variable. Okay. So what we'll say is the channels are discretized, and we know the stationary probability distribution of each of these channel gains. And each transmitter is going to know only its own channel gain. And this is a very important assumption. This is actually not practical, but then in order to do some kind of analysis, we are going to make this assumption that each of these transmitting agents, they know what is their channel gain. In other words, transmitter 1 knows what is H1 and what is the distribution of H1. Transmitter 2 knows what is H2 and what is the distribution of H2, and so on. In real life, this is not actually practical, but we'll make this assumption to start with so that we can do at least some analysis. Right? Okay, this is the formalization of what I was saying. I was talking about sum rate, right, which is the sum of all the possible data rates each transmitter can achieve, and that is going to be our reward. So we are trying to maximize this reward, and we have some constraints. So of course, if there are no constraints, the problem is very easy. So there are some constraints in real life. Real life always comes with constraints. So what is that constraint? We cannot keep transmitting arbitrary power levels. There is a maximum power level that is allowed, and there is also an average power constraint, which means that my battery has certain capacity. I cannot use all the power that is available in the battery, and then I cannot keep transmitting more and more, which means over a period of time t, there is only a maximum amount of power that I can use. And this constraint is basically nothing but the average power constraint. So if you're transmitting over a period t, then in that period you could have transmitted only a certain amount. That amount is equal to the amount present in your battery, and we model that as the average power constraint. Okay. All right. So the problem as of now is to maximize your sum rate. How are we going to maximize the sum rate? That is your data rate, by choosing the right amount of transmit powers. And what is the constraint in choosing this transmit powers? That you cannot choose more than a maximum limit, and you have to choose such that the average of that is within certain limit. This is the problem. Now, if we want to solve this, we want to have a nice closed form expression for this sum rate. If we have a nice closed form expression, then of course we can use our optimization theory and then solve all those things. But then it so turns out that for generalized Gaussian noise, we really don't have a nice closed form solution for computing the sum rate. So our first problem here is to tackle this. What we try to do here is try and come up with better bounds, because we are not able to find a closed form solution or closed form expression for this sum rate. We'll try to bound it, and we'll try to come up with a tighter bound so that it's a good enough approximation. So our first result is to get some upper and lower bounds for this sum rates. Okay, forget about these expressions. All it tells us is that the sum rate is of the form log of 1 plus x. Okay, log of 1 plus ax, where let's say a is your channel gain and x is your power that you're putting in. So if that's the crux of whatever this upper bound or lower bound is. So the sum rate is of the form log of 1 plus ax. Okay, and yeah, so whatever we derived here. So if you're aware of a little bit of information theory, this data rate can be quantified using what is known as the mutual information, which is, in other words, computing the entropies of the involved random variables. What we did was we used this entropy power inequality, a nice inequality that is known in information theory. We repeatedly apply this in order to get this lower bound. So this lower bound is just application of this entropy power inequality, and this upper bound is, again, very simple result. We get this by the fact that Gaussian distribution always has the highest entropy for a constrained mean. So using these results, we get a nice and tight. From our simulations, we see that these bounds are really tight. So, and we can actually prove that the upper and lower bound, as the number of agents go to infinity, almost the gap between them goes to 0. So tight bounds, which means we have a nice objective function, and that objective function is the lower bound that we obtained for this sum rate. And that lower bound is of the form log of 1 plus ax. So all we are now trying to do is optimize this log of 1 plus ax, that is, put in the powers, and the powers are nothing but the a values, okay, such that they satisfy some constraint. How do we model the constraints? We already told that there is a peak power and there is an average power. So we have to model them again mathematically into this framework. The way that we are going to model them is to say that, okay, there is a vector of powers. Each possible channel gain, let's say I have a channel gain h1, then there must be a corresponding power to it. If it is h2, there must be a corresponding power to it, and so on. So for every possible channel gain that a particular transmitter can see, there is an associated power to it. Okay? And that's what we call as a power allocation policy. Depending upon this policy, if the transmitter sees a particular channel gain, it will pick the corresponding power here and then transmit with that power. And given that this is the possible set of powers, we know how to compute the average, because we know the channel's distribution, which essentially means we know the distribution of the powers as well, and we can compute the expected value, right? So the mean of that, that's the average power. So that has to meet our power constraint. Okay? So we have the power constraint here. The set of all possible such vectors which will satisfy our power constraint and such that the maximum value is less than the peak power, we call that as all feasible power allocation policies. So we have to pick a vector from this feasible set, and that is what we are looking for. So we are not allowing all possible vectors here. So we are saying that there is a constricted set, and from this set we'll pick one vector such that when we plug in this expression, we maximize that. That's what we are looking for. Okay, so that's what we have here. This is our objective function. So we have plugged in this vector from this set. So we have to pick a vector from this set such that when you plug in this expression, this entire expression is maximized. So the nice thing that we can observe here is that this set is a convex set. Okay? So because this is a convex set and this is a concave objective function, the entire problem is a very well-behaved concave problem, and it has a global maxima, and you can also prove that it is actually unique. In this case, it's a strictly concave function. So we can also prove that it is unique. So this is our first result, that we said that it is in fact possible to get a unique best possible power allocation scheme that will achieve the maximum. Okay. So one thing that we did here is we said that the power allocation policy is a deterministic map of the channel gain. In other words, if we see a particular channel gain, a particular attenuation factor, we are saying that it is always going to correspond to one particular power. We are not going to say that I'll pick a power from a distribution. I'll not sample a distribution and pick a power from it, but rather I'll pick a deterministic power. The reason why we are not choosing a probabilistic way of choosing a power is that it so happens that a deterministic way is always an upper bound. And the way that you can see that is, take this objective function, or plug in a distribution for the power here, and then we are always trying to maximize the average sum rates. Right? So you take the average of this. So if you apply Jensen's inequality, it will so happen that you will get back this with the average, but that will always be an upper bound, which means the deterministic way of doing power allocation is always an upper bound to the probabilistic way of doing power allocation. Instead of sampling from a distribution for every channel gain, it so turns out that if you deterministically map a channel gain to a power gain, it is always much better than, or it's always an upper bound. So you cannot do better than that. So what we say is, do always deterministic power allocation. Don't trouble yourself with probabilistic power allocation. Do always a deterministic power allocation. Okay, like I said, concavity is really good, which means you can use your regular optimization theory, which means you can use your alternating optimization. You can fix one particular user, or you can fix the rest of all users and then optimize for one user and then alternate from one user to another and find out what is the best possible power allocation vector that maximizes this entire sum rate. This is all good, but what we see here is this is all centralized, meaning the entire power allocation has to be done at the access point, and then the access point has to convey to each of these mobile users, which means there is a lot of computational complexity and computational overhead involved. So computational complexity comes into picture because look at this size of this set. It is huge, right? So it is in fact exponential in the number of channel gains. So computational complexity is first of all really high, and then each mobile phone has to talk to the access point and then say this is my channel gain, and then the channel gain of each of the users have to be collected at one point, and then you do this entire operation at one point, which is the access point, and then again talk to all of these mobile users and then say this has to be your power allocation scheme. So there is a lot of overhead going on if this is done centralized. So the best way to do is decentralized. The moment we are trying to do is, when doing this entire operation in the decentralized fashion, then we have to come up with a better power allocation policy. So we are really not sure what is a better decentralized power allocation policy. Centralized is very clear because of convexity. You pick the maximum, that is very clear. Now if we are going to do this in a decentralized fashion, each user, each agent knows only their own channel gain and their own channel statistics. From this, how are we going to come up with a better power allocation policy? So what we did was, we'll take the simple policy known as a greedy policy. What it does, for all large channel gains, it will use the maximum possible powers till a possible threshold, and below that threshold, it will always transmit nothing. In other words, we are going to transmit always with the maximum possible power when our channel gains are really good, and will not transmit anything when our channel gains are really poor. And how to find out when to stop, that depends upon what is your average power. So we'll say that I'll stop at a point where my average power constraint is met. That's it. So that's all is greedy policy. So this looks like, this is not really optimal. It looks like as if it is not optimal. But it so turns out that if you have large number of users, this greedy policy becomes the optimal policy if there are large number of users, and we can actually prove that. We can say that asymptotically the greedy policy is the optimal policy when all transmitters are transmitting infinitely often. What does that mean? It means that all transmitters keep transmitting and they never stop. If they are transmitting infinitely often, it means that they'll always transmit at any point of time with some probability which is non-zero. Otherwise, you can say that after some finite point of time, they stop transmitting, which means that you can remove that user from the system. And once that agent is removed from the system, then the number of users comes down, and from the asymptotic limit, they start moving to the finite user limit. So it means that we require the agents to be transmitting infinitely often, which means that ensures that we are in the asymptotic regime, and that gives us the optimality of the greedy policy. Okay, I'm going to skip this. Another interesting thing that we showed was that we in fact found the number of users beyond which we can claim that we are in the asymptotic regime. So it so turns out that when we typically talk about asymptotic regime, we'll say that the number of users tend to infinity, right? But then in this particular case, we can say that when n crosses certain threshold, we can say that we are in the asymptotic regime, and we were able to find out what is that threshold. Okay, this scary looking expression gives us what is this n beyond which we can say that we are in the asymptotic regime. So there is a phase transition between the asymptotic regime and the non-asymptotic regime, and we are clearly able to find out which or the boundary of the phase transition, which is the number of users. And till this part, we have not used any kind of learning. It is simply optimization and then trying to solve what is the best way of allocating powers using optimization, nothing more. A little bit of course, statistics. Now, what happens, like I said earlier, is there are practical constraints, right? The first thing that I was saying earlier was that the assumption that each user knows their own channel gain and their channel statistics. But what if each user, they actually don't know what is their channel gain? In that case, we have to do something. And let's say even before that, what if we have fewer users, basically non-asymptotic. In the asymptotic regime, considered multiple access channel where there are multiple agents talking to a single receiver, and then we said the noise is Gaussian, and then we formulated the objective function, which is our total data rate, and then we try to find out what should be the optimal values of the powers which each of the users should use so that we maximize this data rate, right? So this was our problem, and then we said that if all of this is solved in a centralized fashion, it's very easy, simple optimization problem to solve. If not, then doing a decentralized, we use a greedy policy, and we said that in the decentralized version, there are two regimes. There is an asymptotic regime, non-asymptotic regime. In the asymptotic regime, use a greedy policy and everything is well and good. In the non-asymptotic regime, what should we do? Okay? So we didn't know what to do in the non-asymptotic regime because none of these optimization theory really actually works there. So what we ended up doing was we used multi-arm bandits. Basically what we did was each of this channel gain can have multiple possible values of powers which can be optimal for that particular given channel gain. Remember what was power allocation policy? For a particular channel gain, you have to pick a particular power, right? So then each of this power can be seen as multiple arms, and we have to find out what is the best possible arm for a given channel gain. So we run different multiple arm bandit algorithms for each of the channel gains for each of the users. So this is what we ended up calling as state-aware multi-arm bandit problem. So each of these multi-arm bandit problems are run in each of these transmitting users, and as I was saying, all we need to do is we need to find out the power that is corresponding to a particular channel gain. So as and when we see this channel gain, which we'll call as the state, which is known to the user, which means the user is aware of the state, hence the name state aware. They're trying to find out what all possible powers could be plugged in, multiple arms, pick the best possible arm, hence state aware multi-arm bandit. The only problem here is each user will run one instance of the multi-arm bandit for each of these channel gains. So there are hundreds of, or not, there are exponentially large number of multi-arm bandit algorithms running in parallel in each of these agents. Hence, it so happens that the convergence is painfully slow. I'll show you some results. So this is what we call as the state-aware multi-arm bandit. So each user is running multiple multi-arm bandit algorithm for one channel gain, and then they're trying to find out what is the best possible power that is associated with that channel gain. Okay? And of course, the upper bound is the centralized scheme. So it so happens that it takes more than 20,000 number of rounds, and it still hasn't reached, well, we really cannot reach the upper bound, but it goes closer to the upper bound, but it takes painfully long number of rounds to reach this level. So the convergence is really, really slow. So if anyone has some idea of how to speed up this convergence, I'm all ears. We are still working on how to speed up the convergence for this particular setup. So there is another formulation where, as I was saying, what if we actually don't know the channel gains. In real life, there is no way of knowing the channel gains at the transmitting agent. The channel gains may be known at the access point, but not at the mobile phones. So what if the transmitting agent really doesn't know the channel gains or channel values, which is actually a much more practical scenario? Then what do we do? In that scenario, we construct another multi-arm bandit formulation, which is a constraint problem. The constraint comes because, once again, of the power constraint, peak power, and the average constraint. So here, this is like a stateless problem. What we're trying to find out here is not a deterministic map, but now it becomes a probabilistic map for a given channel gain, or what should be the power allocation that each user follows will be a probability distribution. So the distribution is over all possible power values. So there is a distribution over all possible power values. At each and every instant, each transmitting agent will randomly sample from this distribution a particular power value and then transmit with this particular power value. Okay? And what should be this distribution? What is this optimal distribution? And that we compute using the multi-arm bandit algorithm. So we sample from a distribution and then play a particular power and then see what is the reward that we get. One important thing to note here is the reward, even though each user is playing their own multi-arm bandit algorithm, the reward is common to all of them. So they all are interacting through only one common means, and that means is the same reward for all users. So all these multi-arm bandit algorithms, even though they're running in parallel, they're all combined together through the reward. So what happens when we run this algorithm is the convergence is once again a question. So at least the earlier one, it converged at a very slow rate, but sometimes this converges, sometimes it does not even converge. We really don't know what is going on here. We are right now trying to analyze what is going on here, how to prove that it converges, or how to find out conditions under which this converges. That is something, an ongoing problem of ongoing research. So stop here.